Okay, let's talk about continuous functions. And this is exactly what you think they are. They're functions that have no breaks, no jumps. So if you can trace a curve and not lift your pencil off the paper, it's continuous. A function is not continuous where it is undefined. Okay, so for some pictures, here we have a function. This is not continuous because there's a big jump, and that's called a jump discontinuity. This is not continuous, something like this. This is called a removable discontinuity, though, because I can move that point down there and make it continuous. But you see, it's defined at the point, it's just not where it should be because it breaks. And something like this could happen, that's discontinuous. And if we go off to infinity, that breaks. That's not continuous. And likewise, say something like that's not continuous because we lift our pencil off the paper. So let's look at a specific example. First, let's take f of x equal x squared minus 1 over x minus 1. We see that's undefined at x equal 1 because that makes the denominator 0. X squared minus 1 over x minus 1 is not the same as x plus 1. Okay, if two functions have different domains, they're not the same function. It might look like it is because when we factor the numerator and divide out that, we get x plus 1 only if x is not equal to 1. In the first case, the domain for this problem is all real numbers. X can't be 1. The domain for this problem is all real numbers. So it's important that you see that those two functions are not the same. This function here on this side looks like this. This is 1. And if it was defined at 1, this whole would be at 2 because 1 plus 1 is 2. So if it was defined, then the whole would be at 1, 2. On the other hand, this function over here is continuous. This is not continuous. This is a removable discontinuity, though, because we can define this function. Let's say this is how you would treat a removable discontinuity. If we want this continuous, we could say that f of x is x squared minus 1 over x minus 1, x not equal to 1, and 2 where x is equal to 1. Again, what that does is the first function looks like this, and the second one colors in this point 1, 2, so it's continuous. So this function here is continuous. Okay, well, we've done that just by looking at it. The definition, okay, when it says prove something's continuous, you have to go through 3 steps. Number 1, you have to make sure the limit of f of x as x approaches a exists. Okay? Number 2, I'll show you what happens if it doesn't. f of a has to exist, the point has to exist, and 3, the limit has to equal the point. They have to meet, or else there's going to be a break. Okay, so in the first case, what happens if it doesn't exist? Okay, it gives you something like this, because the limit a as x approaches a from the left is this point, let's say L, and this point is M of f of x is L, and the limit as x approaches a from the right is M, so that says that the limit does not exist. They have to be the same. D and E does not exist. Okay, what happens if 2 fails? Let's go over here and see what happens. If if the point doesn't exist, then you have an open circle. So that's not continuous. Okay, so the first one was what if 1 fails. This is if 2 fails. And 3, the limit's not the same as the point. Okay, 3, what if the limit's not the same as the point? Okay, then you have something like this, where the limit as x approaches a f of x is L, okay, because the graph is going to this point as you approach a, but the point itself, f of a, is M. Okay, so the limit's down here, and the point's up here, and they're not equal. So this is what happens when case 3 fails, and that's not continuous because there's a big jump. Alright, so when you have to prove something's continuous, you have to go through those 3 steps. Also, if you want to show that it's continuous from the left, then that would look something like this. I really don't need that. Let's just do it simple. Okay, you're coming in. This is the x-axis. You're coming in. The limit from the left is that. So the limit is this point. And the point is that point. So the limit as x approaches a from the left is f of a. So that's continuous from the left when you get to that point. This is not continuous from the left. So if you go to there, because the point doesn't exist, f of a doesn't exist. And continuous from the right, as long as you have an endpoint, that means the graph's coming in like this. There's A. So you're coming in from the right, approaching that point. This is not continuous from the right. Something like that. Okay, the limit exists, but the point does not. So you can also talk about continuity from the right and the left. Okay, now, we introduce here the intermediate value theorem. And it's really, really important. You've used this in algebra. You probably didn't know you used it. I'm going to call it IVT, intermediate value theorem. And the conditions are that f has to be continuous on a closed interval. Then let k be any number between the y values, f of a and f of b, where they're not equal. Then there is a c, and the x equals c. C is the x value, and the open interval AB such that f of c equals k. So this just tells you that there's a function value for every x in that interval if the function's continuous. And that should make sense. Let me draw you a picture. It says there's a function value for every x in the interval. Okay, here's A, here's B. F of A, say, is up here. F of B, say, is up here. They're not equal, so they can't be at the same height. And we'll get a graph. And so right here is F of A, and right here is F of B. So you pick any k in here. It could be any k in there. Let's pick that one. And we come across, and since f is continuous, there's no breaks, it has to connect, and there has to be a value down here, which we call c. So this point is ck, or c f of c. So f of c is k. It has to connect and find an x value. K is a y value. C is an x value. Okay, so that should make sense. And let me just state this. We're given k. If we're given k, then we have to find the c that goes with it. And we can always do that if the function's continuous with no breaks. Now, what do we use this for? It's really, really, really important. We use the intermediate value theorem to find the zeros of an equation, or some people call them roots. That's where's across the x-axis. So if one of the function's values is positive and the other one is negative, or f of a is negative, they have to have different signs. That puts them on different sides of the x-axis. If one's above the x-axis and one's below the x-axis, then there is a c where the function value is 0. So basically what this is saying, if one y value is above the x-axis and one below, then y must cross the x-axis because it's continuous. It has to connect. So basically, if one's above the x-axis, that means y is positive here, and one's below, y negative, then the graph must, since it's continuous, however you want to do it, it must cross. This is where f of c is 0, and this is your c value. And it doesn't say how many times. It could do it 5 times. It could do it, let's let y here be negative, and here the y be positive. And if we connect them, we can connect them as many times as we want, as long as it's continuous. And there is at least one c where it crosses. It has to cross in order to go from negative to positive or positive to negative. So this is where f of c is equal to 0, wherever it crosses. And that has to happen. So we can find our roots that way. Okay.